In this module, let's go ahead and look at some of the traffic handling features like link bonding, path conditioning, forward error correction, and packet order correction, all included in our SD-WAN subscription license. The first concept I'd like to introduce you to are link bonding policies. Link bonding policies are configured in the business intent overlay. These link bonding policies differ in the amount of forward error correction, path conditioning, and how links are bonded in terms of whether we choose the best quality paths or whether we choose to load balance paths. Details of these are discussed in the Deploying SD-WAN Technologies course. Here is an example of a site with 3 connections. Links can be logically bonded together to create an overlay connection. Remember, an overlay is simply a logical grouping of underlay tunnels. An overlay connection can be configured in various ways to emphasize resiliency or maximize throughput and simultaneously make use of multiple links. In this example, our site has a broadband internet connection, an MPLS connection, and an LTE connection. We can logically bond multiple connections, in this case internet and MPLS, as our primary paths. If the internet connection were to go down, we can still use the MPLS connection. If we lose both internet and MPLS, the Edge Connect can fail over to LTE as a backup and statefully move all the traffic over without dropping a connection. Let's look at a network with 2 underlay tunnels between a pair of appliances. One underlay tunnel goes over an expensive but more reliable MPLS connection, while the other underlay goes over an economical but lower performing internet connection. This is an example of redirecting traffic of different types over different paths based upon the quality of the link. Real-time traffic like VoIP, for example, demands high-quality links because it doesn't tolerate packet loss well. But what happens if that link goes down or begins to experience high packet loss? In that case, the new real-time traffic flows will automatically begin to go over the other link. You can route traffic over the path with the least loss, latency, and jitter using business intent overlays. This example illustrates how when Edge Connect appliances are load balancing traffic across multiple paths. The local Edge Connect distributes incoming packets across parallel tunnels through MPLS and internet connections that are bonded, and the remote Edge Connect reassembles them in the correct order. The screenshot here shows built-in real-time graphing from an Edge Connect appliance with broadband internet and MPLS underlays that are part of a bio. The orange sections indicate where Edge Connect appliances exceeded a desired performance threshold and traffic was rerouted to a more efficient path. You can see that even though the underlays were experiencing loss at various points, the overlay at the top stayed green, indicating that dynamic path selection adapted for changing conditions and kept overall performance in the desired range for this bio. Packet loss and packets arriving at their destination out of order cause problems in the network in many ways. In addition to the slow response resulting from lost packets that need to be retransmitted, which might also further congest an overloaded link, time-sensitive applications like video and voice over IP can suffer from quality and intelligibility problems caused by packets arriving out of order. Most carrier-provided MPLS-based networks have multiple paths with equal costs to any given destination, and the different transmission times over each of the possible paths makes it highly possible that any 2 given packets can arrive out of order. The combination of loss and out-of-order packets can make video freeze and pixelate. VoIP audio quality can also suffer, resulting in pops and clicks, jitter-induced distortion, and lost or dropped calls. In order to correct for the effects of lost packets in your network, Edge Connect offers forward error correction, or FEC, as part of its path conditioning technology. FEC works by creating extra packets containing parity data that it transmits along with the regular data packets over the second best primary link. These extra parity packets can be used by the receiving end to reconstruct missing data if a packet is lost in transit. This is like the technique used in RAID storage arrays to rebuild lost data if a redundant disk goes down in the array. What this means is that you don't have to retransmit lost packets, making your network more efficient. The ratio of FEC packets to data packets can vary dynamically based on the link bonding policy selected. As network conditions change, and as EdgeConnect appliances detect packet loss in the network. So when there is no loss, adaptive FEC utilizes very little bandwidth for FEC. There is some network overhead associated with FEC packets, as they essentially constitute extra packets traversing the network. This means if you're transmitting over a saturated WAN link, FEC could make the problem worse by trying to move more packets across a link that's already full. It's important to know your network and make sure that you have adequate bandwidth available for your needs. Another option for FEC is one-to-one forward error correction. The high availability link bonding policy takes advantage of this with the parallel links to provide extremely high reliability. In this example, we have an MPLS link and an internet link that are logically bonded, and on this link we make use of one-to-one FEC. One-to-one FEC means that we send one FEC parity packet for each regular data stream packet. In this example, the EdgeConnect on the left sends the regular data stream packets over the best quality MPLS link and a 100% complete set of packets across the internet link. In transmission across the WAN, even though there could be substantial data loss on both links, the EdgeConnect at the remote end can reconstruct the entire data stream from the parity packets. You should never even notice the packet loss in transit, because the devices at the remote end beyond the remote EdgeConnect never see it happen. This is the kind of reliability you want for traffic sensitive to loss, like VoIP and video conferencing. As we discussed earlier, packet switch networks like MPLS networks, managed by service providers, almost certainly contain some out-of-order packets. As we can see in this example, out-of-order packets happen because even though packets might be transmitted in the correct order, the individual packets might be taking different paths through the network subject to different latency and processing, which can result in them arriving at the destination out of order. This can cause needless retransmissions because the receiving device perceives that the out-of-order packet has been lost and fails to acknowledge that packet and subsequent packets, causing the sender to have to retransmit. EdgeConnect solves this problem by accurately measuring round-trip time, knowing how long to wait for packets, and caching out-of-order packets. When they all arrive, the local EdgeConnect transmits all the packets on the local LAN in the correct order. Let's go ahead and look at review questions to further enhance your learning. In the next module, we'll take a look at our WAN optimization technologies known as Boost.